Hey, howdy y'all. Well, welcome back to EE360D. Oh, yeah, you guys like that quick presentation I did in the beginning? Alright, welcome back everyone. Today, we're gonna go over state space equations. So, hopefully everyone has already started the first half of the assignment, and if you finished it, then congratulations, less work for you. But if you haven't, please try to get it done as soon as you can, because this next part we're going to talk about is really important, which are state space equations. So what is a state space equation? So if you've realized in your first assignment, well, you probably saw it, you have some output, which is going to be a function of, let's say for our, remember from the transpose, no, it was the direct form 2 block, just using this as an example. It was some internal node Q of n and plus some gains, I guess. If you remembered, I think it was a B, yeah, B's, B0 plus Q of n minus 1. And you see this, and then we would have to solve for our internal nodes, which would be maybe a function of x of n plus maybe another internal node itself. So let me show you. This is the output, current output, and current node. So, and then actually let me note this one. This is previous nodes. And then if you wanted to, there could be a case where this could be delayed to actually, nah, that's a different story for a different block diagram. So with our linear difference equations, you notice that we're solving for our current outputs and current stuff. Whatever we have in the past, we're using the past to determine where we are now. But the cool thing about state space equations, so state space equations, it's basically, how to explain it without making it complicated. We're taking what we know now, as in what do we have in our system, what do we have in our mind, or whatever what you want to put it. Whatever we have right now, and we're going to use what we have now to determine the future. So in other cases, we want to find, let's say, I guess the output, which would be a function of whatever we have, our current inputs. Actually, let me see. I think I may have say that wrong. Plus whatever we have in our system. Actually, I think that's how I want to say it. Q of n plus 1. Okay, this is the part where I get confused. Which is also a function of oops, to re-elaborate, sorry. This right here is what I want to tackle for today. So this is our internal node. Basically what we're doing is we're taking our current inputs, and our current nodes or internal signals, null signal, and we're using this to solve for a future value, future internal signal. So to re-elaborate, we're solving for the next state of a system. We're using whatever we have in our memory right now and predicting the future. So to show you in picture form, all right, let's grab this, page 2. If I were to, so here you have your, let's just call it a delay block. What we've been doing all this time, try an arrow, is here's our internal signal, sig, and then delaying it. So this is probably like some clock, some D flip-flop. And what do we get is we get this delayed signal. However, you know that these D flip-flops are basically, well, it just stores the memory. It stores whatever value is in here. Whatever is here just gets clocked forward. This is our linear diff equation. And then our state space equations is the same block diagram. However, we're going to reformat it as this. So +1. Whatever our next state, or actually, I think I should reword this right. Whatever is our next state will give us our current state. Is that how I want to say it? But point is, we have these pluses. This is what we're going to deal with. So our next state. And then here's our current state. We're trying to predict this using this, but I think it's easier to show it to you in a code. So that's what we're going to be tackling for today. And let's see. So one thing I want to look at, let's take a look. Oh yeah, guess what time it is? Oh yeah, you know it. Let's see. We're going to go over the second part of our assignment, the assignment that I have here. So implementing states systems. And let's see. It says, oh, linear time invariant systems can be described by these little things right here. Our next state, which is equal to current states and current inputs. Then our output, which is equal to current states and input. Current states and current inputs. That's what I'm trying to get to you right now. And then if you look through this, looks pretty cool. What we're gonna try and do is solve for our linear time invariant systems and then translate them into something we can input into Matlab's control toolbox. So I'll show you that at the end. And you can read through this, I'll show it to you. So for exercise 4, so we're gonna do your assignment again. It's asking to generate state equations for the direct form 2 block and the transpose direct form 2 blocks. So in exercise 1, you remembered you drew your block diagrams, right? So you're gonna redraw them again. And then you're going to start labeling nodes because there's differing equations. So should I do the direct form 2 or transposed? You know, just to be different, we're going to do transposed. So let's redraw that. So remembering the equations that we had from the beginning. Let's go up here. There we go. So A0, A1, 2, 3. And then 0, 1, 2, 3 right here. Inputs and outputs, we have 4 inputs, 4 outputs, and 8 gains. So with that information, let's go back here. We will be doing transpose. Well, I can't spell today. Direct form 2 block diagram. Let's use black. So remember the way I told you from that one video, I think it was the introduction to the linear systems, linear equations that I was trying to talk to you about. The transpose direct form 2 is just these, like that. This is the way I imagine it. You guys can imagine it a different way. It's these fingers just goes in. It's really easy to draw. So if I wanted to lightning speed this, like just get this video done with. And then let's just draw this. You're pretty fast, eh? And plus. Oop, we're getting too messy now. And then we have these delays. Have this delay, and goes up. Here's a plus. Then okay, let's just do it. B3. Wait, 0, 1, 2, 3. Forgot one more. B4 plus A4. Let's put the minus there. A3, because I reviewed the notes. A2, A1. Actually, 0, 1, 2, 3. It's like 2, B1, B0, A0, A1, A2, A3. There we go. Someone's gonna get annoyed at that. 3, 3. There we go. And oh, someone's also gonna get annoyed about that too. D. There we go. And then plus, plus, plus. And then this goes here. Don't forget to draw your arrows. Whew. How do you like that speed drawing? So, you see how fast I was? It was really easy. You can draw these block diagrams, and if you want, you can do a mental game with this. Practice drawing these block diagrams as fast as you can. See which one's faster or easier to draw. This one is my favorite one. All 3 block diagrams may or may not be on the exam, so he'll choose from one of them, either DF1, DF2, or trans DF2, and it can either be analog or discrete. So please take a look at your notes. 6 possible answers or problems, 1 solution. So this right here is your direct, transpose direct form 2, x of n, y of n, and let's get to that, and minus and minus. So you're done. Hooray. But we're not done yet. We gotta start doing these equations now. So the way to approach a state space equation, so I'm gonna write that in orange again. State space equations is, from what I just kind of tried to explain, we are taking like a future signal. So this is a future. We're going through a delay, and then we have a current in our state. So that's what I'm trying to explain, but maybe this will make some more sense, or maybe the assignment will make more sense when I try to do it. So we're trying to solve, we're gonna try and make all the equations on the outputs and the next states functions of current states and current nodes. So how do I do it? Okay, let's just tackle this problem. So let's start right here. So we have B0 and A0. Well, A0 is a wire, which is equal to 1. So don't forget that. Actually, let's start here. It's much easier. We have B3 and A3. They come into here, and then they get added. And then what's our output? We will define this node as Q of 3 of n plus 1. Why n plus 1? Well, because n plus 1 is going to be the thing we're trying to solve for our state space equations. If it were the regular version of the difference equations themselves, then this would be Q3 of n. So a little hint for how to solve the linear difference equations in exercise 1. So we have this node. Then what do we have right here? I think I'm going to have room. Q3 of n. Okay, so that's a current state. Our next states, and then it just goes through and we have our current state. I don't know how to explain that as much, but I'll try to keep going and show you what's going on in the code. The code will make much more sense. So now we have a current state. Our current state, and then plus this and plus this. So all these 3 nodes get added to give us a new node. Let's call this one Q of 2 of n plus 1. Okay, that's our next state. So these 3 nodes are current. Okay, actually now it's starting to click onto me. Current, quick purple marker. So let's type x of n. Can you see that? No, it's a bad marker. There we go. X of n, b of 2 is a current input. Okay, it's a current input. And then let me grab a green marker. Let me just grab this node right here. And then minus a of 2, y of, actually we don't want that, which is a current output. But this right here is something I have to tackle later on. We have a current input, we have a current output, and then we have a current state. Okay. So we have a current input, we have a current output, but I underlined this for a reason we'll tackle later. And I have a current state. We have 3 current conditions, 3 current things. What's the next thing? Which is this. This is our next. Next state, the next state that we can have. So add all this, and then what's our next state, which is this. Does that make a little more sense? I think that made a little more sense to me, but oh gosh, I'm trying to see an analogy to explain this to you. But we have current stuff giving us the next state, and now that we have our next state, Q2 of n plus 1, what's here? Q2 of n. And then you start seeing the pattern, and now we can label this node as let's label this as Q3 of n plus 1. And what do we have here? Q3 of n. And now, yeah, that's it. That's all the internal nodes. And yeah, that's about it. So now what I want to tackle to everyone. I thought this would be, because I'll tell you now, all of the 2 block diagrams, the transpose direct form 2 and the direct form 2, have their pluses and minuses. So the reason why I was underlining this was because something was off. There was a red flag that was setting to me. The transpose direct form 2, these next states and these current states, well, let me show you. This current input and this next state, well, these three nodes just equal one node. If you wanted the next state is already a function of current stuff. However, we have this output that I want to tackle, and we'll tackle that right now. So, all right, I got an idea. So remember the last time I was saying, okay, we have water flowing through here. What if we have the running man who is right here in the front, and we throw water, a bucket of water? Where does this water go? So in terms of, well, where it goes, if I threw water here, okay, it's a gain. It just gets added, another gain. This is just a wire, by the way. And it just goes straight to the output. From the input to the output. The minute you just touch this wire, you get an instant signal right here. It's current output, current input, current outputs. Then you throw the water here, and well, it just gets stuck here. There's nothing for it to go. It just stays there. What's the next state? Whatever's here and whatever's here and whatever's here. What's the next? What's this then? And then you start seeing the pattern. Okay, so the water, well, let's say the water is right here now. Okay, it's now here, but it can't go anywhere because, well, what's that next state? Whatever these two are. So we have a current input and we have a current output. However, we don't, in a state space equation, we don't want our state space equations as a function of the output. We want it purely as internal nodes and the input. So the first thing we're going to tackle is, well, what's the first path that the water touches? It's this output. It just directly goes into the output. So we're going to solve for the output first. That was page 3. Page 4. So looking at our little diagram, look at that. What is our output equal to? Our output, let's just write that down, y of n is equal to, well, this is a wire. Actually, I'm just going to write a wire. Just write that as a wire. Is equal to our input, or b is 0, times x of n. So we have a current input, so we're done with that. And now, well, what's this? Plus q of 3 of n. And that's it. We're done. There we go. So for the transpose direct form 2, and if you want, you can look into your notes. So let me pull that puppy out. Let's see. Aha, there you go. See that right there? The transpose direct form 2 is the easiest to solve for the output. The output is super easy to solve for. However, it's the internal stuff that gets really messy. Whereas I think you see a pattern with the direct form 2 block. I think it's right here. Where the direct form 2 block gets pretty messy. Let's see if the solution's in here. Aha, here it is. And I'm encouraging everyone to read this book. I think you'll find it somewhere. The point is, that's our output. So literally, you're done. We have current input, and current state. We're done. Okay. So now we gotta tackle the other problems. So let's get rid of that. So what is Q of 3? Let's solve that one. That's our next state. Q of, oh, wait. This is Q3, Q2, Q2. What am I doing? It's late, everyone. Q of 1, Q of 1, Q of 1. There we go. I'm tired. Q of 1 of n plus 1, which is equal to, well, we're taking a current input. Let's put b of 1 x of n. So we're done with the inputs. Minus a of 1 y of n. Okay, current output, which is a little flag we have to raise. And then plus q of 2 of n. There we go. So for our state space equations, we want our next states to be a function of our current inputs and our current states. But now we have this output. We can't have this current output in our system. We need purely internal nodes and inputs. So how do we get rid of this? That's it. So what we're gonna do is just a quick substitution, which is equal to, let's try this. B of 1 x of n minus a of 1 b of 0 x of n plus q of 1 of n, and hopefully this doesn't bleed through the paper, plus q2 of n. And there we go. And then if you combine like terms to get things into the current inputs and current nodes, so setting that, we have x of n as a function of, well, current inputs, b of 1, then here's our other input, minus a of 1, b of 0. That's it. Okay. And now our next, let's look at the actual states. Minus, got this first node, a of 1, a of 1, q of 1 of n, plus q of 2 of n. Okay, and now we have current input and current states. There we go. And now we're done. Q of 1 of n plus 1. And I'm going to box that. There we go. So now we're done with that equation. So yeah, the transverse direct from 2, yeah, it's a little messy, but that's the price to pay for being the easiest block diagram to draw. So there's got to be a trade-off somewhere. And now let's solve for the next node that we have. It's page 4. Here's page 5. Page 5. The next node we have to tackle is, well, what is Q of 2? Here's our Q of 2. Gotta solve for Q of 2. So here's our Q of 2. Here's our Q of 2 n plus 1. Let's solve for that state now. Q of 2 of n plus 1. Pull this guy out. Is equal to our current input, actually, b of 2 x of n. So our current input times b of 2 minus a of 2 y of n, which is our current output, which we need to fix, plus q of 3 of n, which is this value of this node. And then you start seeing a pattern where we start placing this output and to here. So rewriting it again, b of 2 of x of n minus a of 2 b of 0 x of n plus q of 1 n plus q of 3 of n. Okay? And then combining like terms, we have x of n, big parentheses, b of 2 minus a of 2, because we have this term right here, b of 0, x of n. And then you should start seeing a pattern. And then let's draw the other marker. Minus a of 2, q of 1 of n plus q of 3 of n. And that's it. Q of 2 n plus 1. There you go. And guess what we have? Current input and current states. So now we're done with this equation, and now we tackle the final portion, which is, and I think we can write it right here, which is this last one, q of 3 of n plus 1, our last next state. So the last equation is q of 3 of n plus 1, which is equal to, let's take it slow, b of 3, x of n, which is a current input, minus a of 3, y of n, and then we have no other states. That's it. And then you start seeing the pattern. If you wanted to, you see the pattern? Okay. I want to show you a trick so that you don't waste so much time. The reason why I color-coded it. Look at this. See? Here's our input. And then we have a b2 minus a2, b0. Look at these numbers. Look at that. Okay, does it click anything? b2, a2, b1, a1. Here's a b0. Why do I have another input right there? So, see a2, b0, a1, b0, b1, b2, 1, 1, 2, 2. Is it clicking? So to skip some steps, x of n, b of 3 minus a of 3, b of 0. And then, oh, here's the other pattern, minus a of 3, q of 1. And then here's our current input. And then current state. And q of 3 n plus 1. Oh yeah, if you didn't see this one, as you can see, look at this equation, a1 q of 1, and then there's a state. a2 of q of 1 and q of 1 in some state. a3 and q of 1, and then we don't have a state. See these patterns? I'm trying to show you that, well, if there's any way of memorizing, here are some tricks you can see to help you study for the exam. So now that we have our state space equations, this is a little messy. We have 1, 2, 3, 4 equations, so it's a lot to keep track of. So there's a thing that we can do, and that is we can bundle all this into a happy matrix that we can describe our equations by. Let's put that there. Let's grab page 6. Okay, we're gonna use these sheets of paper to help us solve it. So in a state space equation, the general format, and I'll show you right here, double click. Oh, go. I'll show you it. Our general format is we have an A, a B, a C, and a D, or these Q's and this. Okay. And we're going to try and get our equations in a state where, well, it's easy to read. So let me show you that. Okay, there you go. Double click. So actually, let's try this. So what's our first equation? Our first equation that we have to solve for, and okay, I'll show it to you, is our next states. So we're gonna declare a matrix. Let's call it Q, or should I call it big Q? Yeah, let's call it Q, which is going to equal Q of 1 of n plus 1, Q of 2 of n plus 1, and Q of 3 n plus 1. So we have 3 rows by 1 column matrix, okay? Which is going to be equal to, let's look back at our thing again. We have rows and 1 column. Then we have the square. We're going to have a square right here. So this is going to be at least a 3 by 3. Here's the next states. Then we have this, and I'll show you. So hopefully not, this video is not too long. So we need a square. Okay. So let's grab our Q of 1 equation. Aha, here it is. Q of 1. So we're going to have 3 states. Let's write them down right here. Q of 1, this is how you should be trying to do it. Q of 2 and Q of 3. Okay. So our Q of 1 n plus 1 equation has 2 states. A state of Q of 1, which is multiplied by this minus A1, and Q2, which is just multiplied by, well, 1. So we only have to deal with 2 numbers. So our first number is, well, A of 1. So let's just put an A of 1 right here. 1 right there. So Q of 1 n plus 1 is going to equal, well, this multiplied that gives us, well, this. And then our Q of 2, let's put that right here. And then we don't have a Q of 3. So I don't know if anyone, I hope you guys know what matrices do. It's basically multiplying this and this, and then plus this and this multiplied together, plus this and this. So it just does just like that. Cross this, down there. So, okay. Plus, and now, do we have an input? Yes, we do. So we're going to try and do this. We have 3 equations, and then we just have our input x of n. So in our Q of 1 equation, well, we just have this. Just have our input B1 minus A1. A1 times this gain. I think I wrote that equation too small. B of 1 minus A of 1, B of 0. Oh, this is too tiny. Okay, you guys can just see that. It's okay. But yes, that's our first row. So we just finished our first row. Now let's go tackle on this next one. So here's our Q of 2 n plus 1. I'm going really slow to make sure I show you that this is this is the solution to your assignment. So I want to make sure you guys understand what's going on and why I'm doing stuff like this. Here we have our next state. Let's look at our states right now. We have Q of 1 and then Q of 3. So our Q of 1 is multiplied by minus A2. So here's a Q of 2 equation. Here's a Q of 1. So what do we put right here? A of 2. A of 2, A of 2. Okay? And then we don't have a second state or second node, so let's put a 0 there. But we do have this, and that's just a 1. So let's just put a 1 there. Simple. And now our input, which is B of 2 minus A of 2, B of 0. B of 2 minus A of 2, B of 0. There we go. And we're done with that. And then to finish this off, well, here's our final one, Q of 3, and then A of 3, Q of 1. So let's look at this current node. This is Q of 1, A of 3, which is minus A of 3. And then there's no other states. And there we go, we're done. And now let's look at our input. See the pattern. B of 3 minus A of 3, B of 0. And we are done. And that is our first matrix. So this right here is our matrix A, and this right here is our matrix B. This right here is a 3 by 3, and this right here is a 3 by 1. Okay. So now we're done with that. Now I gotta tackle the output. The output, which is just one output, y of n, is equal to, it's gonna equal current. I should write that down too. Current, current nodes or current state, and current input. So we need, let's do this. Q of 1, Q of 2, Q of 3. There we go. Then plus, I think it should be fine. Actually, this one should be the easiest. There's literally just one equation. This right here. There we go. We only have one state, which is Q of 1. I don't know why I did this. There we go. So Q of 1, which is just multiply by 1. Pfft, we're done. Okay, bigger one. And then 0 there and 0 there. There you go. This is your matrix C. And then, let's see. How big is this last one? It's just, I think it's just a 1. 1 by x of n. Yeah, just one input. And what is our input? Just b of 0. And that's it. The transpose direct form 2 has the easiest output. It has the most painful current states, next states equations to solve for. So this one's probably the more challenging one for the state space ones. Tell me how the direct form 2 one goes out. And now we're done. Oh yeah, I should put the D right here. So now you're saying, okay, we just did a lot of hand calcs. This is just a lot of work. Do you understand what's going on? We have a current output, which is equal to current inputs and current states. We solve for our next state equations, next state. Next state using our current inputs and current states. You're seeing the pattern, current input, current states, current input, current states, and next states. There we go. Is it all trying to click? And then we just all wrap all this. Here's our next state. We solve for our next state and our output using current states and current inputs. I'm trying to repeat myself a lot to make sure this gets into your head that we're trying to solve for next states and current outputs using just internal nodes and the input itself. which is going to be useful for a future assignment that we'll be doing. Now, how do we program this? First, let's grab out our pieces of paper. And this should be easy because we've already developed some code for this. And here's our assignment that we've always been doing. So, computer assignment 2. Buddy. And let's see. What does your assignment say? So, just paste the pictures that you've already. So, you're going to redraw the block diagrams, and then you're going to do exactly what we have right here. Write your nodes, and then box your equations. If you please try to give it to me. Give me the answers in terms of matrices. Let's do it in the matrix form because hint, that's what Dr. Stuber would like. So if you do it like this, that'd be excellent. But if you do it like this is also fine, but please just box your answers. So you can put this all into one page and then use this equation or this function that we developed to paste your pictures into Matlab. So now to tackle on the actual assignment. So that's exercise 4. Easy points, well, heavy points. It's a lot of drawing, a lot of equations. This will be graded really heavily, so make sure you understand exercise 4 and exercise 1. So please practice them. So now let's look at this. Using a for while loop, we're going to use fors. Write programs. So you're going to have to rewrite your programs based on what we did for exercise 4. So to make this video as simple as possible, exercise 4, actually let's just skip that. Implement your equations. Exercise 5a, actually 5 exercise 5, yeah, let's just do 5a. And now let's create the program. So remember from our previous video how we developed the direct form 2 block diagram? So we're gonna kind of have to reuse this code right here. So what we're gonna do, and yes, I'm gonna do this actually, let's just copy this, maybe copy that too, we'll edit it. So if you haven't seen why I did this for our time and why I did this, please check out the previous video for more information. Why do we have this? Why are we pre-allocating memory? So everything from the first video we are reusing. So please hopefully review that video, and I do this too. And yes, because we've developed a really powerful code, we can just reuse the for loop. And all we have to do is just punch in whatever we have right here. So let's just get rid of this. Let's pull out our first equation. Our first equation is this. So we're going to punch in this equation that we have here. So we're just going to solve for our current output, y of 1, and I, our current output, is equal to actually let's do q of 1. So we got to pre-allocate memory for these 3 nodes. 1, 2, 3. Okay. Q of 1, and the current input or current state plus b of 0 dot times qx of I. There we go. So this is our current output. And now we can solve for the next thing. Q of 1. So where does the water flow? The water flows, the next closest node is this. So the next thing we're going to be solving for is the next state of Q of 1. So Q of 1's next state. Oh, drop that piece of paper. Q of 1, 1I plus 1 is equal to minus, actually let's do this, b of 1 minus a of 1 times b of 0 dot times x of 1 minus 1i plus, or actually this is minus a of 1, I think this is fine, q of 1 and 1i plus q 2 1i. There we go. And this is our next state. There we go. And then to copy paste and finish this as fast as I can. There we go. 2 and 3. So if you've noticed a pattern from what I've told you earlier, see this? B1A1, B2A2, B3A3. Here's a B0, B0, B0. And all we do is just look at this. You see the pattern. See? Okay. Just to, oh, I touched my piano. B2, B3, A2, A3, and then B0. Okay, actually I should probably, yeah, that's fine. Then A1, A2, A3, this stays the same, and then this last one, let's get rid of that, get rid of that, and that's it. See this pattern? This is the reason why I organized it like this. You can see that there's a pattern. We have our current inputs, we have our current states, and yeah, that's it. We're done. I think we can run this too, and then let's call this one figure 70. There we go. And here's our Kronecker delta. And now what do we do with it? I think we can run it now. Hopefully it doesn't bark at me. Please don't bark. Oh, it did bark. All right, undefined input. Okay, Matlab, okay. Oh, it ran. And that's it. This is our next state. This is our state space equations. And we don't need that. Get rid of that. And then let's put a 3 right there. Put a 3. Put a 3. Put a 2. Put a 3. And let's run that. And okay, because someone's probably super OCPD right now. You can use a set function if you don't like squares. If you don't like squares, you can make a wider rectangle, or maybe even better, you can make it taller. 6 or 7. Let's make it 8. Actually, that might be too tall. Let's make it. Okay, let's make this one 7. You like that? Now it looks more taller, you can see it. And if you've noticed, this system looks really similar to what we've done in exercise 2A for the transposed, the rect form 2 block diagram. And there it is. And if you're really OCP about this, actually, let me grab that other one. It's already developed. Boom. Slap, slap. So, and I should probably title this. Actually, I'll retitle that. SS, boom, run, click, boom. So if you've noticed, this chronicle, we're dealing with the same equation. Nothing should change. So this is our filter. This is some op-amp we developed. We're just transcribing it like 2 different ways, but it should give you the same output. So what I'm saying is, this direct delta, when we're throwing it into the system and into all these block diagram programs, you should get all these pictures should look the same. So this is the direct form 1, 2, and 3. Well, transverse direct form 2. You have to develop these equations, by the way. They should all look the same. And click on that, get these numbers, get those numbers, and could show you what that actually. Let me show you. See this number 0.254459. 254459. What's that number mean? I have to tell you this right here. Show you this. And here it is. 2544. Is that what I said? Yeah, 59. See this number right here? B0. Okay. Where is that graph? I need to show you practically what's going on. Oh, there we go. When we throw water in here, what is B0? It's that 0.254459. Just directly goes into the output. And that's what you're seeing right here. What's the first thing at n is equal to 0? What's the first value? 0.254459. Is it making sense now, everyone? All right, so now congratulations, you've developed the program for the transpose direct form 2. So now you can just change your input and have some fun with that. Actually, let me show you this. Yes, I'll show you this because I want to show you something cool I did. Let's grab this cosine, and you can just change these outputs. Actually, cos 2, whatever. I want to show you something. The reason why it's a filter. Plus cosine of 0.6 times pi dot times n. And now we're gonna copy this, actually cos 2, and then just place it into I'm too lazy. Okay, what? Okay. Oh, because we haven't declared the unit step. Where's the unit step? Unit step. If you can't find the unit step, what do? Double click here and find where you've instantiated it. There we go. Boom. Then copy that. Go down here. Boom. Boom. Ah. So we just did right now part D, which is a really slow signal plus a really fast signal. So you get this mess. You get noise. So fast signals are usually noise, and slow signals are the signals of interest. And our filter should ideally get rid of that pesky fast signal. And now we get our cosine wave back. So in case you didn't know how to do that. So now let's go tackle the final part, which is probably what people are panicking about. So we're going to use Matlab's built-in functions to solve our homework, or that's computer assignment. Exercise 6, and this should be fun. Use the controls exercise 6A. So how do you approach this problem? So from the controls toolbox, we're going to be dealing with the SS equation, which if you don't know what it is, type in here CLC help SS. If you look right here, SS just creates an actual state space right here. So as in this right here is our next state, but it's our derivatives, which is the analog version. And then it tells you, okay, right here, actually, it should tell you right here, discrete time state space model. So if you put a 1 right here, it creates the actual difference equation version of this system right here. So we're gonna have to put a 1. That's how you get the discrete mode. To turn on discrete mode, put a 1 right here, and that's what we're gonna do. Let's copy this. There we go. So it's asking for A, B, C, D, and T of S, which we can set to 1, or actually T of S, 1, discrete mode. Comment. There we go. So where do we get these A's, B's, C's, and D's? And that's the reason why the wait, actually let me grab it. Recently, right here. Aha. Oh. That's why we did a lot of work in the beginning. Remember this? The next state, these matrices, we already have them. A, B, C, and D. Now how do you program this? So let's type in A, which is equal to, and I'm gonna do it a weird way. So do minus A1, or yeah, minus A1, 1, 0. Okay, actually. Okay. And then I'm gonna do this, dot, dot, dot. This dot, 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 these 3 dots creates a new line. So the next line will be the continuation of this line. So minus A2, actually, there we go. A2, 0, 1, dot, dot, dot. Then minus A3, 0, 0. There we go, and that looks like a square. If you don't put these right here, then you have to do this. And this looks kind of weird, or messy to look at, or I don't know. If you like this, you can do this. But I like this. Like, see, you can see the square now. Don't forget your semicolon. Actually, don't semicolon them, because then these print out. Or if you want, you can use fprintf. But I would like to see everyone print this out to show that, hey, I know what's going on. Okay. And what's this barking at me for? Terminate. Nah, we don't want to terminate. B. What is B? B is equal to this jumbled mess. So let's do that right now. Let me copy this. Boom. Boom. 1, 2, 3. And copy this. Boom. 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 Then 2, 3. 2, 3, and we're done with that. Now let's go to vector C. Why do we have this? C, which is just equal to 1, 0, 0. So you can just type in 1, 0, 0. And D is equal to be a 0. Really simple. Be a 0. And that's it. So now you have your state space equation. What does this do? Boom. And now you have a state space equation. And if you want to see it, click on that. Now we have our equations that we can solve for. Now what do we do with this system? We've already developed the system. Our system. So now let's do stuff with it. Let's do an impulse response. The Kronecker delta is just an impulse, which is the beginning of the next couple of chapters we'll talk about. An impulse is just a kick. We're going to kick the box. And if you look at our function, the impulse response, just look at our system, take our system, and then we'll look at the first couple samples of our system. In this case, we're going to look at, I think, N. I think that's what I typed in. Yes, I think so. Yeah, let's look at it. So, Y, M, SS, something like that. Yeah, let's call it YSS. This is equal to impulse sys. And we want to look at do I want to length of n? There we go. Yes, let's copy this. Yeah, let's copy this. Call this one figure. Go. Let's look at the input, which should be a Kronecker delta, yes. And then let's look at the output, which is YSS. Controls. Just type in that. And there you go. Boom. Something's barking at me. X must be the same length as Y. Let's click on it. Doesn't like this. N. So what is this? 55 by 1. I know why. Run. There we go. Because we don't use, I got it. And oh no, come on, come on. And get rid of and okay. 0 to 50 plus 50, okay. 0 to 50. Okay, 51. Okay, what does it want? 52. Okay, let's give it 52 then. 0 to 50. 53. Oh. There we go. So here's our input. Then we kick our box. And let's look at these numbers. Actually, why did I do that? 2, 2, 1, 2. Let's grab this position. Boom, boom, run. There we go. And then let's compare this figure to something we've already done. Here's our impulse. Actually, that's not our impulse. Impulse. Hopefully everyone edits these codes. Let's type in this right here. Boom. Here we go. Here's our input. Then look at this right there. Here's our previous answers that we have, and here's our state space. It starts at 0. And look at that top number, 480302. Let's look at n is equal to 10. They match. And then you can see a similar pattern for everything else. If you want to do the step response, all you do is just change this to a step. The unit step is a step response. And then the inputs, well, let me show you the inputs. If you wanted to do an input, you can do the same. Actually, I'll show you this. You can do this. LSIM, the system itself, the input x of 1, which is the step, and then I guess we can do this, and yes, we can. And it's the same thing. Stimulation will start at a non-zero. Yes, that's fine. And what do you see? They're the same. So yes, you can either do the impulse function, or if this LSIM stuff makes more sense to you, you can do that too. And yeah, this should be a really easy assignment other than for this exercise 4. So is this really helpful? I'm doing this assignment because I had a student who was like, oh my goodness, I can't do the Matlab. I'm like, are you watching my videos? No. Are you coming to class? No. Are you doing anything? So I'm taking the time to show you what's going on, to maybe help you. If this was helpful, tell me. If it wasn't, then also tell me. I'm trying to show you that Matlab is a very powerful tool, and you'll see once we get later into the semester with Laplace and the Z transforms, you're gonna start loving Matlab and do it, use it a lot in your daily lives. So with that, that wraps this video. So actually, if you guys wanted to, I can show you a quick demonstration. Are we playing? Everyone was trying to wonder how I played those drums. I'm using a, what do you call it? Is it gonna let me drag it up? Using a music program. Alright, y'all. Take care.